Hello everyone and welcome to our video tutorial where we would be discussing and studying opamp characteristics, that is CMRR and slew rate. Talking about CMRR, CMRR stands for common mode rejection ratio and is an ability of an opamp to reject the signal common to both the input terminals such as 60 Hz noise. It is the ratio of differential gain to common mode gain, that is AD over ACM. Ideally, gain in common mode configuration is 0, hence ideal value of CMRR should be infinity. Apparatus required: CRO, BNCs, connecting wires, multimeter, set of resistors, breadboard, function generator, DC source, 741 IC. The circuit diagram that we will be using today. We have just placed 741 IC over a breadboard, and from the positive pin, that is pin number 3, we have connected RF to the ground. Now from the positive pin we are connecting R1 to the V input. From negative pin, that is pin number 2, we are connecting R1 to the input channel. Now from the negative pin we are connecting RF to the pin number 6, that is the output pin. Now from function generator we have taken our input source and we have placed it along the resistors R1, and the other wire of that BNC cable is grounded. Now from the channel 1 of the CRO we are taking in the wire and placing it along the parallel of the wire we have taken from function generator in order to measure input in the CRO. Now from pin number 6 we are connecting another BNC into the channel number 2 of our CRO in order to measure the output. Now it's time to apply minus 15 volts to the fourth pin of our IC, that is minus VEE, setting up the ground connections, applying plus 15 volts to the pin number 7 of our IC, that is plus VCC. Case 1, that is R1 equal to 100 ohm and RF equal to 560K. Note down that channel 1 and channel 2 are at 1 volt. The upper waveform is our input waveform, whereas the lower waveform is our output waveform. The upper waveform can be adjusted through Y shift 1 and our lower waveform can be adjusted through Y shift 2. Calculating the upper waveform, it's block number 1 and then it's block number 2 and it's then block number 3. V in is 3 into 1, that is 3 volts. V output is block number 1 and it's 1.2. V output is 1.2 volts. CMRR equal to R1 plus RF over R1 into V in by V out. V in we just saw that it is 3 volt and V out is 1.2 volt. RF was 560 kilo ohm and R1 was 100 ohms. So CMRR is 14002. CMRR in dB is 82. Case 2, R1 is 100 ohms and RF is 760 kilo ohms. Measuring as our input, it is block number 1, block number 2 and block number 3. V input is 3 into 1, 3 volts, and V output is 1.8 into 1, that is 1.8 volts. CMRR equal to 12668 and CMRR in dB is 82.05 dB. 3, that is R1 equal to 100 ohms and RF equal to 890 kilo ohms. Measuring input at 3 blocks again, that is 3 volt is our input voltage and V output is 1.4 volts. CMRR equal to 19073 and CMRR in dB is 85.6 dB. We just practically observed and calculated CMRR. Now it's time to simulate it over multisim. Under component group and analog, place 741 IC over the console window, and under basic, place pairs of resistors, that is R1 and R2 as 100 ohm and R3 and R4 of 560 kilo ohm. Now place function generator and CR on console, and under the sources place VCC and minus VEE on the console. Set them as minus 15 volts and plus 15 volt respectively. Now connect the one terminal of R4 and R2 and to the positive terminal, that is pin number 3, and connect then R1 to the R2 and then apply V input to both of them. Then connect R1 and R3. From the channel A of the CRO, connect to it to the function generator and the channel B to the output pin. Connect R3 to the output and the negative of the function generator to the negative of channel A and channel B. Now from components, find out the ground and place it on the console window. Now it's time to simulate our circuit. Since it is complete, double click on the oscilloscope, reverse the mode. Now change the time base. Set the position. So this is our desired output, and this is very much similar to what we practically observed on CRO. Upper one is our input waveform and lower one is our output waveform. This was all about CMRR. Now talking about the slew rate, when it comes to the speed of the amplifier, slew rate must also be taken into account. The slew rate of an amplifier is the maximum rate of change of output voltage, and it's typically specified as volt per microsecond. In order to reproduce a signal without distortion, the amplifier must be able to change the output just as fast or faster as the input signal of the interest. We just placed 741 IC on breadboard and we are grounding pin number 2. We are applying the inputs to the pin number 3, that is the positive pin, and taking the output over pin number 6. We are connecting BNC from the CRO now. Now it's time to apply plus 15 volts to the pin number 7 of 741 IC, setting up the ground connections and applying minus 15 volts to the pin number 4, that is minus VEE. Note down that channel 1 is at 5 volt and time base is 50 microseconds. This is our waveform due to the delay, and taking the straight line down, we would be just calculating the time. So it's 0.2 volt and it's 0.4 volt and it's 0.6 volt and it's 0.8. So time is 0.8 into 50 microseconds. Slew rate is del V by del T. Del V is 28 volt, as voltage across an opamp cannot exceed 28 volt due to plus minus 14 volt of swing, and time base is 50 microseconds. So del T is 0.8 into 50, that is 40 microseconds. So our slew rate equal to 28 by 40 microseconds, that is 0.7 volt per microseconds. We just practically observed and calculated slew rate. Now it's time to simulate it over multisim. We just placed 741 IC on the console, and now we are placing our function generator and connecting the positive pin out of it. Now we would be placing minus VCC and plus VCC on our console and connecting it to the pin number 4 and pin number 7. Connecting the negative pin of our function generator to the pin number 2. Now we are placing ground and connecting it to the negative. We have taken oscilloscope and connected our 6th pin to the channel A of oscilloscope and the negative to the ground. Now changing the value of VCC and VE to minus 15 and plus 15 volts. Our circuit diagram is completed. Now it's time to simulate it. Double click on the oscilloscope and reversing the mode. Now adjusting the time base. Adjusting the scale of channel B. So this is what we get output for slew rate, and this is very much similar to the output we got on our CRO while doing it practically. So this was all about slew rate, and for the next time you need to select an amplifier and you are concerned about the speed, you must consider the slew rate of that amplifier. Thank you for joining us for this video tutorial and hope you understood the concept of CMRR and slew rate. All the best.